convert back to Hilbert space, it's actually pretty straightforward. We just need to remember what we mean when we see a Liouville space operator operating on a Liouville space vector. This corresponds in Hilbert space to the commutator with that operator, right? If it was the Liouvillean, it's the commutator with the Hamiltonian. We just don't use the H twice. But for every other kind of operator, we're going to just use the script version. All right. So what we're going to do here is we're going to write then our Hamiltonian, sorry, not our Hamiltonian, that was fresh in my mind, our response function using this instead. All right. So basically all it means is going through all the terms that we have and figuring out how to do the commutators. Right. So it's actually not hard. All the time points that we wrote in there before, plus I over h bar to the n, the Heavisides. So this is not going to change. And then the good stuff. All right, so the good stuff is we're going to have now an ordinary, you know, what do you want to call it? An ordinary Hilbert space interaction picture operator. This was the one that got shifted all the way to the end, essentially, right, by the G that was there. Then this is going to commute with all the other V's that are nestedly commuting, right? So I think we worked out one of these kinds of examples before where you have, you know, if you have V of T1, V of T2 on rho, right? So let's just do one out for the heck of it. So T2 plus T1, V of T1. Now, of course, it goes to 0 first. Okay, so then we have 0. Rho EQ. All right, what this turns into is going to be V of 0 commuting with rho. Okay, that's sort of step 1. Then we have this commuting with that. So V T1 commuting with that. This commuting with that. So it's actually easier than it sounds to write it out. Right? And then so on. All right, just keep doing that. So it looks exactly like what I just wrote. I'm going to write the first or the last term, however you want to think about it, the one on the left. Tn minus 1, T1. And then we have that commuting with a whole bunch of different commutators. And I'm probably going to run out of space, but let's see what we can do. T1, V of 0, rho EQ, and then a whole mess of closing of these square brackets. That's that, and then close it. So this is a single expectation value of this operator. Okay, now we're back to operators, right? Because we're talking about Liouville space. So the idea is that the commutators are, in the way you can think about this is that they're acting like to the right. So we have this, then this, then this, then this, then this. All right. So what we can also do is we can rewrite this however we want. Not however we want. We can rewrite it in a slightly different way. Okay, so this expression, certainly the one that seems like it makes the most sense. It turns out the one that we want to use is going to be slightly different. And I want to show you how we do this. So at this point, at the point before, where we have the expectation value with the V on one side and all the V's in the row, we could have ended up with this equation by operating with the V to the right, like here. But we could also have operated with the V to the left. So the way you might write that would be, we have that left side, right, which was V tau n plus tau n minus 1. And then we had the V of tau n minus 1 plus tau n minus 2 and so on. And the next V, right? And then all the way down, dot, 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 rho EQ, like that. This is the expression that led to this. We went this way. We could also go this way. Okay, so let's figure out what happens when you do that. So the way we go to the left is the way we always go to the left, which is we go to the right and we take the adjoint of that. So to make the same thing that would be going to the left, we would take the adjoint of this, and that's going to make it go to the right. Okay, so the way we do that is we write V dagger tau n minus 1 right, plus all these things. And then this is operating on V to the right. This thing adjoint is the same as this right here. Okay, so there's a lot of terminology, a lot of stuff here. So let's just call write this in a slightly simpler way. I'll call this V with the script, and I'll call this A. Right, this is some Hilbert space operator, which becomes a vector in Liouville space. This is a Liouville space operator. So we're interested in what is V A dagger, right? Well, we know what V does to A. V takes the commutator with the Hilbert space version of V, right? So this is going to be the commutator V dagger A. Oops. Right? And then adjoint again because we need to get back. Okay, so what we can do is we can write this out. It's going to be V dagger A minus A V dagger. Right? So now we just have to remember what does dagger do when you have a product of operators. You take the dagger of each operator and then you switch the ordering. Right? So that's going to be A dagger V, because daggering a dagger just undaggers it, minus V undagger A dagger. All right, so this is the same thing as A dagger V. So you see when it goes to the left, we switch the order of the operators in the commutator. Now this is also equal to A V if it's Hermitian, which it is. It's a dipole operator, which is Hermitian. Okay, so when we put all this together, what we find is that we can write this equation in a different way, which is to say we can start with the commutators on the left. So we'll have still, this is an expectation value. The first term will be this one commuting with the commutator with this one. And it maintains the order because of all the stuff that we just worked out right here. The A is playing the role of this V. This V is from the script V. So we have V Tn plus Tn plus minus 1, and so on, commuting with V Tn minus 1. So that becomes like the first term. And I think, yeah, what am I missing? Of course, I'm missing all of the additional ending brackets that'll be there. Because now this is going to be commuting with the next one. Right? So the next term that you might write is, dot, dot, dot. And it's going to go all the way to the last commutator, VT1. All right. And then what's on the outside now, instead of the outside being this V here, multiplying by all these commutators, we have rho EQ operating on the net effect of all these commutators. Right, so this is the only sort of, I would say, this is the tricky part, figuring out what happens when you want to do a Liouville operator to the left. When you bring it back to Hilbert space, you just have to remember to switch the order of the commutator, because of the fact that the commutator, the adjoint of a commutator, switches the order. If the operators are Hermitian, then you can just replace them with the same operator. Okay, so essentially we have finished. Okay, so this equation here, if you have the Mukamal book, is 516b. This is 516a from the Mukamal. And then it's equivalent to the equations I wrote before, which were the previous ones, which I didn't list them, were, I'm just looking at my notes here, I think 514 and 515. All right, and the difference is these ones are in Liouville space, and 516 is in Hilbert space. All right, and so it's pretty common, I would say, to consider, once we've done the thing in Liouville space, to come back and do calculations in Hilbert space, but it's not required. Remember, they're just two sort of styles. There's a few things that are easier to see directly when you go into Hilbert space, in Liouville space, but some things are just as murky in both spaces. All right, so we'll use whatever is either more convenient or is what is found in examples or the literature. So just to tell you where we're going next, as you might guess, we're going to use these expressions in whatever form is most convenient to look specifically at, for example, special cases like P1, P2, the second order polarization, and P3, the third order polarization. And just to give you a little bit of terminology, so this is going to be obviously the linear optical response. This is responsible for example, linear absorption. The second order response is going to make a polarization that is responsible for things like second harmonic generation. And that is going to be useful, for example, for spectroscopy of interfaces, where it turns out that the second order response is only non-zero if there's a broken symmetry somewhere. So we might call this like second harmonic generation, some frequency generation spectroscopy. It's not two-photon absorption, and I'll remind you about why that is because remember, to make an excited state population, which is what you're usually thinking about when you're, okay, so sorry. Yes, it could be two-photon absorption. What I mean to say is it's not two-photon fluorescence. Two-photon fluorescence is the most common way one of the most common uses of multi-photon absorption. And in two-photon fluorescence, we actually have to make an excited state population. Remember we talked about earlier on in the course, if you want to make the system be in a population, you need two field interactions. And we're going to see how this is super obvious when we use a density matrix when we use a diagrammatic representation of a density matrix evolution. All right. Here we have the chi3, or the third order response. And this is responsible for this is the most general sort of, every system could have this response for a symmetric system, a centrosymmetric system. This is responsible for palm probe and multidimensional spectroscopy. But actually, it's also responsible for fluorescence. So we're going to see how fluorescence just arrives or comes out of this. All right. So the next step is that we're just going to write down some response functions. We're going to see how, when you add up all these, we're going to list every single term that gets added together to make the actual response function. So all the commutators, that's going to give you a bunch of different terms. And then you'll see that each term, each commutator, the commutator leads to a set of terms, and each term can be written down diagrammatically so that you can actually map out what are the different states or the different populations and coherences that are visited along the way to making that signal generated. And what's nice about that is many of them will have pretty good interpretations in terms of experiments that people do. And that will sort of give us a stopping point for what I consider the sort of the existential nature of the spectroscopy. Why do we have the signal in the first place? And then what we're going to do is we're going to move to another sort of section of the course where we consider what goes on in between in some sense, the field interactions. What does the system do so that if I excite to an excited state, it doesn't just stay there forever, because we know that doesn't happen. Or if I make a coherence, if I make a linked quantum superposition of two states, that doesn't last forever either. So how do I get these things to go away? How do I get excited energy to go away? How do I get coherence to go away? And the way we're going to do that is we're going to make a model for relaxation, which is going to be, for our class, the red field theory. All right, so we're going to develop red field theory. We're also going to come up with more of a, let's say, a stochastic phenomenological model for various kinds of relaxation phenomena. And to do that, we're going to develop what's called the Kubo model, the Kubo line shape model. And that's going to allow us to classify the nature of spectral broadening into two limits. One is the so-called homogeneous limit, and the other is the inhomogeneous limit. All right, and those are simplified versions of this. Gives you something called the optical block equations, which is used commonly in like NMR and in atomic physics to just treat the dephasing and the relaxation of simplified systems. Some of those ideas are just fine in chemistry, but we know that they're too idealistic to apply to true real systems. All right, and so as we go and develop these different spectroscopic techniques, I'll also show you how we can look at experiments people do and classify what they've done. And we'll talk about what these different relaxation processes are and how we can understand something about how a system is coupled to a bath. And that's in some sense the real reason that we want to use a density operator, is because we can have a bath at finite temperature and we can add in a new kind of ignorance, which is to take into account a lack of complete description of the dynamics of the bath. And that's very important for giving us our red field equation. That's the equation of motion for the system degrees of freedom when the system is weakly coupled to a reservoir. All right. So that's where we're going. And as you will see, most of the kinds of spectroscopy that people do can be reasonably characterized or categorized in this framework.